Hi guys, welcome back to Calculus with Mr. Robeson. All right, today we're going to look at some derivative notations and we're going to look at how derivatives and continuity affect each other. All right, so we have a lot of different notations for derivatives. So we went over the ones last time with f prime of x, and we also said f of x plus delta x minus f of x over delta x. We can also use the letter h instead of delta x. That's a pretty common notation. A little change in x, we often just use h. We also had delta y over delta x. That's approximately the derivative. So that's not just necessarily the derivative. That means approximately derivative. If we just have dy over dx, though, that does mean the derivative. We can put d over dx. This is the notation meaning take the derivative. All right, and this would work if y is some function of x. Then this would be the notation dy over dx. So the y goes on top, the inside variable goes on bottom. If you wanted to say df over dx, we don't use that a lot, but you could use that. If we take the limit as x goes to 0 in the delta y over delta x, then that is exactly the derivative. But if we just write delta y over delta x without the limit, that's approximately the derivative. All right, we can also write y prime. So that's kind of like the lazy way of doing it. But that only means that x is your variable. So that means dy over dx. If you had a different variable than x, you don't want to write y prime because that means something else. All right. So if we've got the variables t and s instead of x and y, well, t would be like our x, s would be like our y. So that means the t would be on the bottom, the s would be on the top, and that would be ds dt. All right, like that. All right, for this next one here, we've got theta and r, which is polar notation we'll learn about later. But again, this works like our x, this looks like our y, so the r goes on top. So dr over d theta, change in r over change in theta is what that means. There's our derivative. All right, so here's one for you. So if we're using the points n and p as our variables, so n is our independent, p is our dependent, our y variable. What's going to be the notation here for the derivative? All right, so let's see, the p is our y, so dp is going to be on top. N is our x, our independent variable, so that goes on the bottom, dn. So dp over dn is our answer. There it is. All right, so let's do some more work with derivatives. So f prime of x here is what we want to find. So that means it's the derivative of f of x if x is, or if our function is just the square root of x, and then we want to use it to find the slope at all these different points. So the slope of the tangent line is what we mean when we say the slope. So we need to find f prime of x, which is the limit as delta x goes to 0 of f of x plus delta x minus f of x all over delta x. If you want, we can do this one with h instead, because I know a lot of people don't like to do the delta x, so we'll try it with h instead. As h goes to 0 of f of x plus h minus f of x all over h. All right, so that would be, our function is the square root of x, so we get the square root of x plus h minus our just original function, square root of x. So our original function is always just kind of sitting over here at the end that's being subtracted, all over h. And this is the limit as h goes to 0. All right, the way we simplify this, if we tried to plug in right now, we could plug in 0. We'd get square root of x minus square root of x, which is 0 over 0. So that's indeterminate. So what we do is we multiply by the conjugate. Whenever we have square roots, the conjugate's usually a good bet. So we get x plus h plus the square root of x. And we're going to do that on the bottom too, x plus h, square root of x. On the top, we're going to get x plus h minus x. All the middle terms cancel out, all the square roots cancel out. On the bottom, we don't want to do anything. We're just going to leave it there. Square root of x plus h plus the square root of x. These x's are going to cancel out, x minus x. We've got an h and an h divided by h. We're going to be left with a 1 on top. So we're left with 1 over all this stuff, square root of x plus h plus the square root of x. And then we want to take the limit as h goes to 0. So this is 0. We get square root of x plus square root of x. So we get 1 over 2 square root of x. All right, so there is our derivative. That is f prime of x. All right, so now we can just plug in the x values to get our slope. So to get the slope at 1, 1, we do f prime of 1, which is 1 over 2 times the square root of 1, or just 1/2. If we want f prime at 4, well, that's 1 over 2 times the square root of 4. Square root of 4 is 2. We get 1/4. If we want f prime of 0, we get 1 over 2 times the square root of 0, 1 over 0, which is undefined. So our derivative does not exist there. All right, that just lets you know the derivative does not always exist. All right, we'll see later on where it doesn't exist and where it does exist, but it doesn't exist there. All right, let's try this other guy here. We want the derivative with respect to t. So we want to know what's dy dt. So t is our variable. Then use it to find the tangent line to the curve at t equals 1. All right, so dy dt is going to be the limit. We'll stick with h because I know people like h better. As h goes to 0 of, let's see, we got this function with t plus h plugged in minus just the original function, 2 over t, all over h. All right, the way we simplify this would be a common denominator, so we need to multiply this guy by t top and bottom, so times t times t. We're going to multiply this one by t plus h top and bottom. All right, so we're going to get 2t minus 2 times t plus h all over this common denominator, which is t times t plus h, all over h. The h is really just going to move up here. We still have the limit happening. All right, if we distribute the 2 here, we're going to be able to cancel some stuff out. So we have 2t minus 2h over t times t plus h times another h. These 2 t's are going to cancel. This h and this h are going to cancel. And then we take the limit as h goes to 0, so that h goes away. We've got negative 2 on top and t times t, or t squared, on the bottom. So that is our derivative, dy dt. All right, and we want the tangent line at t equals 1. We can just plug in 1. So dy dt when t equals 1, that's one way we can write that, is negative 2 over 1 squared, or negative 2. So there's our tangent. There's the slope of the tangent line there. All right, we want to find the tangent line though. So we've got the slope, we need a line. So to get a line, we need a point and a slope. So we're going to plug in 1, because it wants the line here. We get 2 over 1, which is 2. So we get the point 1, 2. So we've got a point and a slope. So we get y minus the y value equals the slope times, well, we usually use x, but t is our variable, so t minus the t value. We don't have to do anything. We can leave that. That's the equation of a line right there. Done. A lot of work there. Don't worry, guys. It'll get easier. All right, so continuity. So another form of the derivative, it means the same thing. We can write it like this, especially if we want it at a point, f prime of c. So instead of the x plus h and stuff, it's just f of x minus f of c over x minus c as x goes to c. So this is another useful form of the derivative. All right. So what this actually gives us, though, is that if the function is differentiable, so if this exists, then it must also be continuous. All right? The reason why that is if this limit exists, well, this value would have to be equal to this value. All right? So that means the limit as this x goes to c is equal to f of c. All right? So that means the limit exists, that means f of c exists, and they're equal to each other. All right? That way that we can be able to factor and cancel out a 0 here. If we weren't able to do that, because x is going to c, we get 0 on the bottom, it wouldn't work. So if this derivative exists, that means this top can be factored, and this top, these two parts will equal each other. So if it's differentiable, it is a continuous function. All right, but it doesn't work the other way around. So just because it's continuous does not mean it's differentiable. That's the big mistake people make. This is a one-way statement. So differentiability implies that it's continuous. So if you can take the derivative and plug in the point, it's continuous there. But if it's continuous, it doesn't mean you can always take the derivative. However, if it's not continuous, like if there's a jump or a hole, that means it's not differentiable. So let's take a look at the next slide here. So we got lots of jumps here in our step function. So everywhere there's a jump at all of our whole numbers, we cannot take the derivative. All right, so the derivative at 1 here does not exist. All right, so f prime of 1 does not exist. My prime kind of got buried there. All right, at a corner. So on one side, the slope is -1. The other side, the slope is 1. So right here at 2, well, we're fighting. From each side, it should be different things. So if it's the limit definition is different from each side, that means the limit does not exist there. So this means f prime of 2 does not exist, right? Because it's at a corner, right? Sometimes we have corners where they're curved. So curvy corners have a fancy name. They're called cusps. You can just call them corners. That's fine. All right, and we've got another odd place where they don't exist, which came up on the square root function. All right, we have some vertical tangent. So the tangent line, the slope of the tangent line is infinity right here. It's infinite. So the derivative does not exist there. So for this guy, let's say we're using g, so g prime of 0, well, that's not 0. Well, yes, this function would be at 0. If we took the derivative there and tried to plug in 0, we'd have some major issues. Does not exist. Because this is x to the 1/3 looks something like this, like that. So it has right there, it has that vertical tangent. That's a problem. All right, so we looked at more derivative notations. We looked at a second formula for the derivative, and we looked at how derivatives and continuity work. So derivative existing implies continuity, but the other way around does not work. And the other definition could be useful. Limit as x goes to c of f of x minus f of c over x minus c. Whenever it asks you to take the derivative, you can also try and use this at that point c. This will also work, so you can use that whenever you want. All right, we'll practice it some more next time. All right, so that's it for today. I'll see you again later.